So let's read a little bit about Diffie-Hellman protocol. So the idea is to exchange cryptographic keys in the not secure channel, in the public channel. So let's see how it works. So both parties, Alice and Bob, agree on a large prime number P and a generator G. And remember that a generator is a number that can generate every number in the group, such that G is a primitive root module P. These values are public and can be shared openly. So we have the generator of the group and a prime number P. And P is known to both Alice and Bob, and also G, the generator, is known to both Alice and Bob. Now, Alice and Bob each choose a private key. Both are just random integers. Now, Alice computes G to the A, mode P, and Bob computes G to the B, mode P. Now they exchange, this goes to B, this goes to A, this goes to Bob, this goes to Alice. And now they both get S by raising it to the power of, look at this. If I take this, but A is the private key that Alice chose. B is the private key that Bob chose, right? Now, Alice creates G to the A, Bob creates G to the B. Now, G to the A goes to B, and G to the B goes to Alice. Think of it, what happens if now I take G to the B and raise it to A. A is the private key of Alice, so she can, and I take G to the A to Bob and then raise it to the power of B. You are getting, maybe I need to show that, G to the power of B comes from Bob, and now what Alice does is creating B times A. This is Alice. This is this one. Now, if you look at Bob, he gets G to the power of A, right? This is what Alice sent him. Now, you take it with B. Now, when Bob multiplied by B, or take to the power of B, this one here, it creates again the same one. Now, if you look, Alice and Bob now they both have the same secret. Now they both have the same secret, cryptographic key over a channel. Now you can use this key for encryption, because no one else, except for Alice and Bob, no one else knows this S. And don't think that it is easy to get A or B. Remember the discrete logarithm problem? So you can see here, what I did here is to show you that Alice and Bob created the same secret key, which is called S here, because all what we did. Now, you may think that, okay, what's the problem? When Alice sends this thing to Bob, someone, the attacker, can get it and get A. And if he gets A, for example, when Bob sends it to Alice, he can get it and just take it to the power of A, like Alice does, and get the secret key. Yes, what's the problem? The problem here, that even if the attacker intercepts this one or that one, he won't be able to get B or A, because the discrete logarithm problem. And this problem in a closed set tells you that it's hard to get this. It is hard to get this here. it is very hard to get this x. We need to find each such z by trial and error or using approach. We found that it's difficult. Difficult discrete logarithm problem lies in the fact that for large prime number there is no known efficient algorithm to solve it. This is what is suitable for cryptographic application. The best known algorithm for solving the DLP, discrete logarithm problem. Just a sec, I have something. Okay, so let's continue. So this is how Diffie-Hellman can create a secret key in both parties throughout the public area without this secret key be known to anyone else except the two parties that share the secret key. And all this is happening throughout the public area. I mean, they send almost the public key throughout the area. Now, as I said, someone can intercept, for example, this or this because it is sent in a public area. So the question is why? Why it is safe? It is safe because when it gets to A, remember we are taking this to the power of A. Now, if someone, remember that A and B are random integers, that A is created in A and B is created in B, if someone could intercept it, it would be very hard for him, even though he intercept it, to get A. Even though he know G, even though he know P, because remember that does the public can know P and G and still a Diffie-Hellman protocol will be safe? See that if even if the public can know the P and G, still the Diffie-Hellman will be safe. This is because of the discrete logarithm problem, because even though I know P and G, to solve this, if I know this value for A is very hard to solve, and he gave example here, to solve this, even if I know this one and that one and this value, this is the G, this is the P, and even if I know this value, to solve this for x in a finite set is very hard. So no, because of the discrete logarithm problem. So you saw this is not an easy problem. There are no good algorithms to solve this problem. So for someone, even though we go throughout a public area, it's very hard to get A and B, small a and small b. So even though someone will get this, for example, he won't be able to take it to the power of A because he doesn't know A. Or this one, he won't be able to take it to the power of B because he doesn't know B. So he won't be able to create S, the secret key between the two. Only Alice and Bob will be able. Alice will can because she will get G to the power of B. Just add A here and you get the secret key. B will be able to do that because you will get G to the power of A. Just add his B and you get the secret key. Now there is an example here. Let's do it. So here is the public parameter. So namely, everyone knows the parameter P, which is the prime number. We are working in a mode P in a finite set of pp will be prime number, and we have the generator. Again, generator is a number in the finite set that can generate every other element in the set if you take it to the power of 1, 2, 3, 4, 4, 4 until you are creating all the sets. So this is generator. This is an element that is called a generator in the finite set. Now A chooses a number, a random integer number, 6. B chooses a number, a random number, B, call it 15. Now the public key that Alice create again, it's the generator, G, we called here, to the, wait a sec. Okay, um, so we understand why it's very hard for someone to do that, and we are in example. So here is the A that, we have the P, we have the G, we have the A, PG, which are general. Bob and Alice just say they are agree, and everyone knows it. Now, a small a is a random integer that Alice created, and small b is a random integer that Bob created. Those are the private key of each. No one will know that. A only Alice will know, B only Bob will know, and they share their public keys g to the power of A mod p, g to the power of b mod p. They share those with everyone. Everyone knows that. But still, no one, because of the discrete logarithm problem, no one will be able to efficiently get this small a or this small b. 6 is a, 15 is b. So if someone will know small a or small b, he will be able to create the secret that Bob and Alice will create. Because if I get a, I will take this one to the power of a and get the secret key. If I get small b, I will take this one, take it to the power of b, and will create the secret key that we will just create here. So they exchange those public keys, and then what each of them do is take this to the power of their secret key. So Bob sends 19, which is which is g to the power of, let's call it b, and Alice takes this g to the power of b, which is the 19, and take it to the power of small a, which is g to the power of b a, g to the power of b a. Bob gets this 8, which is g to the power of small a, and take it to the power of b, and again he gets g to the power of ab, which is the same as g to the power of ba. They both get the same number. And this is the shared secret key that no one knows except Alice and Bob. So this is how Diffie-Hellman can help us share or create a shared secret key throughout the public key. Everything almost is known to everyone, but because the discrete logarithm problem, no one can intercept small a and small b, the variables that the random numbers that a created and b created, each a created in a and b created in b. Okay, and now they tell you that the man in the middle attack or parameter selection, poor choices are lead to vulnerability, because if you are taking something that is very easy, someone can work throughout the discrete logarithm problem, and even though it's hard to tackle, someone may be able to tackle it if the P and G are not very good. Diffie-Hellman is public key cryptography used in communication like SSL and TLS. Okay, this is about Diffie-Hellman, how we can use public area, even though it's public, to share secret key between two parties, and using the discrete logarithm problem. Thank you very much. If there are any mistakes or correction, please tell me. And thanks for Mistral to create me the nice summarization so I can use it. I wish that you understood how it works. Again, we have generator and the P. Our group is of the size of P. P is prime. G is the generator. We create a small variable, random number for Alice. We create small b, random variable for B. No one knows small a and small b except for Alice and Bo respectively. G to the power of a mod p is what Alice creates. G to the power of b, small b, mod p is what Bob creates. They share it throughout the public area, and no one can intercept small a or small b because of the discrete logarithm problem. It's hard to do that, let's say. You need to pick G and P as needed, and very good. After they share it, each one of them raises it to the power of their secret, private, their keys. a small b. Alice create g to the power of ba from Bob getting g to the power of b. Bob getting g to the power of a, take it to the power of b and create g to the power of ab. So both created g to the power of ab mode b. So both have the same secret key using the public area to create this. This is the Diffie-Hellman algorithm. This is the idea. This is the importance of the discrete logarithm problem in Diffie-Hellman algorithm, to share secret key throughout the public key. And this is why it's used. Thank you very much. If there are any mistakes or correction, please tell me, and I'm sorry, and that's it.